This is the first part of the electromagnetic induction lessons. Part one, we're going to talk about Faraday's law. We've seen so far that a moving charge in a magnetic field experiences a force. We saw this that when the moving charges are contained by a wire, the wire experiences a force and moves. This is how the motor works. And then we've also seen now that if the moving charges are not contained in a wire, they will start to move in circular motion. What we're going to look at today is explain how a moving conductor in a magnetic field can cause a current to flow. This is the whole idea of induced current, and it's how we generate electricity. Some simple demonstrations you might have seen in the lab. Here we've got a very sensitive ammeter, possibly a galvanometer would be used to measure very small changes in current. If we take this wire and move it up or down inside the magnetic field between this horseshoe magnet, then you would have seen that a current flows, and the direction of the current depends on whether the wire is moving up or down. You can also have the same effect and get larger currents by making the wire into a coil, and you can move the magnet in and out of the coil, and this will cause a current to flow around the wire. In both of these you could move the magnet and keep the wire still, and here you could move the coil and keep the magnet still. It doesn't matter which is moving as long as there's some relative movement between both. But hopefully you saw in these demonstrations how electricity, in its simplest understanding, you are generating electricity by moving a wire in a magnetic field, and this is the essence of electromagnetic induction. So a summary of very initial simple findings. An EMF is induced if the coil, wire or the magnet or both move. As long as there's relative movement, you get an induced EMF. The size of the induced EMF depends on how fast you move it, the size or the magnetic strength, the number of turns if it's in a coil. You should have seen that in the lab. You can change the size of the induced current by changing those things. The direction of the induced EMF, whether it's positive or a negative, depends on the direction of movement. And in the previous examples we did have a complete circuit, so there was a complete wire with an ammeter in, and if there is a complete circuit you get a current flowing, so the induced EMF causes a current to flow. So what is electromagnetic induction? Well, this is Michael Faraday. He came up with the ideas and the formulas behind electromagnetic induction, and we're going to just get to a point where we will have some formulas, but mainly in today's session is to look at the ideas that he came up with to see if we can understand them. This is a schematic, if you like, of what we've got to talk about. Here I've got a wire. This wire, I'm going to call it's from P to Q, so it's a length of wire. It's got a length L, and it's in a magnetic field, so you can see the lines of flux, and it's in a flux density of B. So B is, if you looked in this area here, the flux density, the amount of lines of flux you've got. This wire is moving in it, and the wire is going to move from its current position. If I just click, it's going to move it from its current position down to the bottom position. So there aren't two wires, it's one wire moving through the field and actually cutting through the lines of flux. So if PQ moves down, the electrons move with it, so all the electrons in this wire move down as well. So they are all electrons moving in a magnetic field. Now each of those electrons will experience a force, and that force pushes them towards the end Q. If you want to prove that, you can use Fleming's left-hand rule, but you've got to remember that an electron moving down the screen is like a positive charge moving up the screen. So you can use Fleming's left-hand rule to show that they all go towards the end Q. This causes a voltage across the ends of a rod. It's a source of EMF. You're going to have loads of electrons at one end, or more electrons at one end than you have at the other. So you've got a potential difference across this wire. If you attached a cable, if you attach the end of Q to P, you would have the electrons moving around the circuit. So if you sort of had a wire and that wire was joined up the ends there, then you'd go from having a potential difference or a source of EMF, you'd actually have a current flowing around the wire. If there's not a complete circuit, then you just end up with effectively an EMF being induced. Now, if there was a complete circuit, conventional current would flow from Q to P. If you think about it, if the electrons are moving from P to Q, that means that conventional current would flow the other way around. So we need to sort of think carefully about which direction the current will flow in a moment. So there is another rule. Some students don't particularly like to remember both because they get confused, but if you want to work out the direction of the current, as just mentioned, you can use what's called the dynamo rule, or Fleming's right hand rule. It's obviously using your right hand, and this works out the direction of the current when there's a movement of a conductor in a field. Now, similar in that your first finger's magnetic field B, the force that you put in this time, because remember you're moving the thing, so the thumb is the direction of the force, and the direction of the induced current will be shown by your second finger. If you want to go back in the video, you can apply this to the previous diagram and it should check out. It's kind of the opposite of the left hand rule because it's taken into account conventional current as opposed to movement of electrons. Okay, so how are we going to sort of put some terms on this? Faraday's model of electromagnetic induction we've just seen, it's all about how it's cutting the lines of flux. So that bar as it moves down, as it's moving down the page, it's cutting through the lines of flux. So you can think of the electricity is generated or an EMF is induced when lines of flux are cut by a conductor. If you look at this little picture at the bottom, if you've got a bar magnet and a coil, if you move the magnet into the coil, these lines of flux will be cut by the coil. Now I've got it moving, but it's not brilliant because you can't see through it. But if you imagine all these lines of flux here are going to cut through the coil as it goes. So because there's more lines of flux cutting through, there's more coils being cut, so they'll each cut through 1, 2, 3, 4, 5 coils, you get more EMF than you would, say, in this more simple setup at the top of the page. Okay, the idea of flux cutting is fairly straightforward. There's another way of describing this, and the reason you need this is because the exam formulas talk about a concept called flux linkage. Now, it's very similar, it's exactly the same, you can argue, but rather than talking about the number of lines of flux cut, you can consider the change in flux linkage. To do this, if you imagine I've got one coil of wire from A, and if I move this coil of wire from A and I move it towards the left hand side of the screen so it's in position B, you can see that it's going to cut through new lines of flux. So if you have a look here, it's going to cut through this line. Let's just put a pointer on. It's going to cut through there. It's going to cut through there. So it's going to cut through that one as it moves. It's going to cut through this one as it moves. And at the bottom here, it's also going to cut through that one as it moves. So you can see it's cut through 3 lines of flux. But you can also do this in terms of a change in the flux that's linking the coil. So what we mean by a flux linking, let's try and highlight these, flux linking the coil. Here we can see that the lines of flux that actually pass through or link the coil are, there's 1 there, 2, 3, 4, 5, 6. So all of these lines here actually pass through the coil. Now if we look here in position B when it's moved, this time we've got 1, 2, 3, 4, 5, 6, 7, 8, and we've got 9 of them that now link or pass through the coil. So we've got a change in flux linkage of 6 to 9. So it's a change in flux linkage of 3. Exactly the same idea as flux cutting. 2 different ways of describing the same thing, but you need to understand the term flux linkage because that's what's used at A2. Okay, so in summary really, how do we increase the size of this EMF? This was the first idea of a single conductor moving through a field, cutting the lines of flux. This is slightly more complicated where you've got a bar magnet that's being moved and many lines of flux cut through the many turns on the coil. And then we had this idea of flux linkage where moving this single coil from A to B changes the flux linkage. In all of these ideas, the size of the EMF can be increased by using a stronger magnet. Why? Well, a stronger magnet will have more lines of flux because it will increase, they'll have a greater flux density. So the more lines of flux or the greater the flux density will mean that more lines of flux are going to cut the conductor. You could use a coil with more turns of wire. If you've got more turns of wire here, then by definition, more of them are going to get cut, so you'll have a greater EMF. You could use a coil with a greater cross-sectional area if you sort of capture more or link more of the magnetic field, then you end up with a much greater EMF. Or you can indeed move it faster because you increase the rate of change. So if you increase the relative movement between the coil and the magnet. So in summary, this is Faraday's law. The induced EMF in a circuit is equal to the rate of change of flux linkage through the circuit. At the start of this little video, I didn't say that because it's difficult to understand what we mean by the rate of change of flux linkage, but I'm hoping now that you can see what we mean.